Hi viewers, so welcome back to the lecture series on state space modeling. So far we have learned something about the state space modeling in 6 lectures. The first 4 lectures were focusing on the modeling of various physical systems as a state space model. So we took electrical and mechanical systems in that, and we understood that any physical system can be represented in this form. The first equation we call as the state equation, and the second equation we call it as an output equation. So these two equations together form the state space model. So what is interesting is any physical system is now reduced to 4 matrices A, B, C and D. So if I know these 4 matrices, I get the model of any physical system. Okay, so that is what is the attraction of the state space model, and of course I'm able to take more number of variables which vary with respect to time within the system. So those variables I represent as the state variables in this vector, state vector. And in the fifth lecture, we understood that if this state space model represents a particular physical system, and if I got another transfer function model for the same physical system, since both of them represent the same system, I should be able to transform this state space model to the transfer function model and the transfer function model to the state space model. Okay, so how a state space model can be transformed to the transfer function model is what we learned in the last class. So if I have a state space model of this, then the transfer function model is given by y of s is equal to g of s into u of s, where g of s is equal to c into si minus a inverse b plus d. Okay, so from that expression I can get the transfer function model for the system. So if it is an SISO system, g of s straight away gives me the transfer function, and if it is an MIMO system, instead of getting a transfer function, I will get a transfer matrix where the size of the matrix is decided by the number of outputs and the number of inputs. Okay, so the size of the transfer matrix is going to be m cross r. So this is what we learned in the fifth lecture, and also along with that we understood that the eigenvalues of the state matrix is same as the poles of the system or poles of the transfer function. So this matrix contains the characteristic equations. This matrix. So this matrix is nothing but the state matrix. State matrix contains the characteristic equations. Since the characteristic equation roots are the poles of the transfer function, then directly we say that eigenvalues of this state matrix is nothing but the poles of the transfer function model. Okay, so these are the things that we learned in lecture 5, and in lecture 6 we did some numerical problems to understand the concepts a little more. Okay, right. So obviously in lecture 5 and 6 we transformed the state space model to a transfer function model. So I told that if the transformation from state space model to transfer function model is not possible, then the transfer function model also can be transformed into a state space model. Okay, yeah, logically it should be true, and that is true also. And in this next 2 lectures we are going to see that. So how a transfer function model can be transformed to a state space model. So but before going into that exactly, there should be something in between. To understand the concept or to understand how this transfer function can be transformed to a state space model, we need to understand certain other things. They are nothing but the similarity transformation and also the canonical forms of the state space model. Okay. So before actually going into the transformation of a transfer function model to a state space model, we'll see something about the similarity transformation and the canonical models. So this lecture is going to focus on these two things, that is similarity transformation and the canonical models. Okay, so let us take this state space model. X dot is equal to ax plus bu and y is equal to cx plus du. I think you should be well aware that x of t, u of t and y of t all are vectors, where x of t contains n number of elements arranged as a column vector, because it contains n state variables, and u will have r number of input variables, and y will have m number of output variables. So all these x of t, u of t and y of t are all vectors. So if x of t is a vector, I can transform this x of t into another vector x bar of t using a transformation matrix P. When I say this, some of you may not understand, or you will ask me how. So to understand this concept in a better way, I have taken a 2 cross 1 vector. I have taken a 2 cross 1 vector. So it is, the elements are 7 and minus 9. Okay, so this is a 2 cross 1 vector. Now, this 2 cross 1 vector, can I write in terms of some other vector? Yes, I can do it. 7 minus 9, I can write it as a product of a square matrix and another vector. See, 7, 9 is equal to square matrix 1, 2, 3 minus 4 and another vector 1, 3. So you can try with your calculator, just multiply these two, this matrix and this vector, you will get this vector. And I can again write this 7 and 9, this vector containing 7 and minus 9, as a product of another vector and another matrix. That is it. So I can even use infinite number of matrices to transform this 7 minus 9 vector into some other vectors. I can write in infinite number of ways. Okay. So what you will be able to see here is, I have a vector 7 minus 9. I am connecting this 7 minus 9 to another vector 1, 3 through a matrix, through a square matrix. Yeah. So now the question is, this is one vector and this is another vector. This, the second vector, whether I can get from the first vector. Yes, I can get. How? For example, 1, 3 is nothing but inverse of 1, 2, 3 minus 4 multiplied by 7 minus 9. Okay, inverse of this multiplied by 7 minus 9. So you can again verify, you will get back 1, 3. So I am able to connect two vectors using a transformation matrix. Isn't it true? Yeah. So in that case, I can call this vector as x. I'll call this vector as x bar, and I will call this matrix as P. Now I can write it as x is equal to Px bar. Isn't it true? Yes, it's true. But only thing is, for this transformation to be bidirectional, that is, if I should get this 7 minus 9 from 1, 3, and again if I should get 1, 3 from this 7 minus 9, this matrix should be invertible. If inverse for this matrix doesn't exist, I cannot find out the inverse of this matrix, then this bidirectional transformation is not possible. So what is the condition for a inverse of a matrix to exist? The determinant value should not be 0. The determinant value should not be 0, and that means that matrix should be a not singular matrix. So this P matrix should be a non-singular matrix, and therefore P should be an invertible matrix. So if I have an invertible matrix P, I can write any vector x like this. Okay, so I mean this x is transformed to x bar using the transformation matrix P. Using the transformation matrix P. Okay, now hope you will agree with me that x, x of t can be written as P into x bar of t. Okay, so if that is so, now I can use the transformation here in the states matrix. See, I will write this state space model as x dot of t. See, x dot of t is now P x bar of t, the whole dot. That is differentiation of this entire thing, because x of t is nothing but x into x bar of t. This I can write it as, since P is a constant matrix, I can take this outside and I can write it as x bar of t dot P into x bar dot of t. So if I use that notation, I can write it as P x bar dot of t is equal to a p x bar of t plus b u of t. Please note that there is no change in the input vector. And here in the second equation, this x of t changes to p x bar of t. Since this x of t changes, y also will change. So the changed output vector, I will call it as y bar of t plus this doesn't change. U of t, I am not making any change. Okay. So what happens? If you look at the state equation, the left side has got x bar dot of t multiplied by a matrix P. If I want to get some other state space model in the same structure as this, I should not have this P matrix here. So what I can do is, I will just pre-multiply all the terms in the state equation by a P inverse. So what happens? P inverse P is an identity matrix. It goes away and the other things remains the same. Okay. So now I will use some notations. So instead of this P inverse AP, P inverse AP, I will use the notation A bar. So this entire thing can be written as A bar. And this P inverse B, I will write it as P bar. So P inverse B, I am going to write it as B bar. Okay. The CP, I will write it as C bar. CP is equal to C bar. And this D, I will write it as D bar just for the sake of uniformity. Please note that D bar and D are the same. Okay. So this is the new equation, new state space model, or I can call it as this is the transformed state space model in terms of the matrices A bar, B bar, C bar and D bar. Okay, where A bar is given by P inverse AP and B bar is given by P inverse B and C bar is given by CP and D bar is given by D. Okay, so doesn't it look like almost, not almost, it's the same, in the same structure. This state space model is in the same structure as this. So this is what I call it as a transformed model. Transformed model. Okay, fine. Now we got this transformed model. Well, now the question is, I had a physical system. I modeled it using this state space variables, or I modeled it in state space. I got this model. Now I have transformed this to this model. So the question is whether this model, this mathematical model, this state space model represent the same system, which this particular state space model represented. That is the question. That is what we are going to examine now. Okay. Yeah. So when do you say that these two state space models represent the same system? So what are the things that characterize a system? First thing is the characteristic equation. Okay, the characteristic equation should not change. And the second thing is, obviously, if the characteristic equation does not change, the eigenvalues will not change, because eigenvalues are the poles of the systems are nothing but the eigenvalues of the system, and they are the roots of the characteristic equation. So if the characteristic equation doesn't change, there's no change in the eigenvalues. And if the eigenvalues doesn't change, then eigenvectors are also not going to change. Okay, so that's the first thing: characteristic equation, eigenvalues, and the eigenvectors. Then the second thing is the transfer function which I will be able to derive from this model and this model should be the same. If I am able to get the same transfer function from these two models, then I say that this system also represents this. This model also represents the same system represented by this set of equations. Okay. And the third thing is the input-output relationship. If I give u of t, whether I use this model or this model, I should get the same output y of t. Okay. If that is true, then I can say that these two models represent the same system. Okay, right. So if these two models represent the same system, I can call this transformation as a similarity transformation because similar. The models are similar. Okay, so this transformation I'll be able to call it as a similarity transformation. So in next few minutes, that's what we are going to examine. We are going to examine whether the characteristic equation is going to remain the same, eigenvalues, eigenvectors, and of course the transfer function represented by both the systems, or whether they are going to remain the same. Okay, right. Let us take the original state space model first. Ax of t plus bu, y of t is equal to cx plus du. Okay, so the characteristic equation for the system is obviously a determinant of Si minus A, that is Si minus A equal to 0 is the characteristic equation. And what about the transfer function? Transfer function is also given by C into inverse of Si minus A into B plus D. Okay, so these are the characteristic equation and the transfer function model for the system, original system. Okay, right. Now let us consider the transformed system, that is x bar t is equal to a bar x bar of t plus b bar u of t, and y bar of t is equal to c bar x bar of t plus d bar u of t. Okay, yeah. Now for this system, what is going to be the characteristic equation? So let us examine. The characteristic equation for the transformed model is going to be S I minus A bar, because for the transformed model what we have is the A bar. S I minus A bar determinant is equal to 0. Okay, so now S I, what is A bar? A bar is going to be P inverse A. P inverse A P determinant equal to 0. But at the same time, since I got P inverse and P is here, I can write this I also as a P inverse P, because when I multiply the inverse of any matrix with that matrix, I am going to get an identity matrix. Okay, I'll use this principle. So any identity matrix can be either represented as A inverse A, or it can also be represented as A inverse. But since this substitution favors me in the the simplification of this equation, I'll be using this. So this identity matrix I is represented by P inverse P. Now if you look at this, P inverse is pre-multiplied in both these terms. Please note that S is a scalar. So since P inverse is pre-multiplied, I can take it outside. That is P inverse I can take outside, and P inverse, and similarly P appears on the, it is post multiplied also. I can take the other side. So ultimately if I take this P inverse and P outside, again it is going to be identity matrix here. So inside I will have S identity matrix, okay, identity matrix minus A, because this P inverse is taken outside and this P together is also taken outside. This entire determinant is going to be 0. Okay. Now, if I have got two matrices, the overall determinant is nothing but A determinant into B determinant. This is from the matrix theorem. So I can, take individual determinants here. P inverse determinant Si minus A determinant and P determinant equal to 0. What is the determinant of A inverse? It is nothing but 1 by determinant of A. So therefore, this I can write it as 1 by P inverse. Sorry, P, 1 by P, determinant of P. Obviously, determinant of P is going to be a scalar quantity, and therefore I can cancel these two, and what I get finally is Si minus A equal to 0. Isn't it the original characteristic equation or the characteristic equation of the original system? So, even if I use this transformed model, if I find Si minus A bar, ultimately what I am going to get is the same characteristic equation what I will get if I use Si minus A is equal to 0. Right? So therefore, the first point is the characteristic equation doesn't change. If the characteristic equation doesn't change, then the eigenvalues also will not change, because the roots of the characteristic equation, we call it as the eigenvalue, and the eigenvalue doesn't change, and therefore the eigenvectors also will not change. Now the question is, what about the transfer function? Whether the transfer function changes. So, what is the transfer function? G of S is equal to C S I minus A the whole inverse B plus D. Okay, so for this transformed equation, it should be all bar. Now let us substitute the values. C bar is equal to Cp. Again, as I said, this identity matrix, I write it as P inverse P. This is P inverse AP, the whole inverse. This is B matrices, P inverse P. Okay. P inverse B plus D matrix is simply D. Okay, now let us see. Can I take this P inverse outside as we did earlier? Cp. So please note that is an inverse sign here. Therefore, P inverse Si minus A, as I did previously, I am going to take both P inverse and P, pre-multiply by P inverse and post-multiply by P. Okay, the whole thing inverse P inverse B plus D. Hope you are aware of A B inverse is equal to B inverse A inverse. Or if I have another matrix also, C inverse, then it should be like C inverse B inverse A inverse. It should be inverse. That is from the matrix there. So if I apply the same thing, Cp, so Cp into the first inverse, what should come is the inverse of this P. So inverse of this P, then the inverse of this matrix, Si minus A inverse, okay, and the inverse of P inverse. Inverse of P inverse is nothing but the P. And what remains here is P inverse B plus D. See, this becomes an identity matrix. This also becomes an identity matrix. So I can write it as C into Si minus A the whole inverse B plus D. is it in the same transfer function as the original system? Yes. Okay. So therefore, I can say that both these models are representing, the same system. Okay, the same system can be represented by these two state space equations. The original equation of the transform model represent the same system. And in the same way, I can show that the input out behavior also will not change. So that is why I'm going to call this transformation as similarity transformation. Okay, so similarity transformation. Now, you may ask you, why do you do all these things? Why this similarity transformation? Why this similarity transformation? Okay, so I'm going to explain that. So how do you transform x of t is equal to, I put it as p into x bar of t, and I get these four transformed matrices. The beautiful thing is, for some specific values of p, for specific p matrix, if I use those specific p matrix and transform this equation into a new transformed equation, then the structures of A bar, B bar and C bar are interesting, or they result in a fixed structure. They result in a very interesting, standard structures for some specific values of P. If I use a specific value of P or P matrix, these matrices look beautiful otherwise, I can say. Okay, or they will have a specific structure. Okay, that is what is interesting. And what is interesting about those structures are they are very useful in certain analysis. They are very useful in certain analysis. Okay, if I look the structure itself, I can say that whether the system is good or bad, something like that, or maybe in the future lectures we are going to study about the controllability and observability especially. And if I look at the structures of this transformed matrices, then I will be able to say immediately whether the system is controllable or whether the system is observable. That's the beauty of this transformation. So now let us, it is a time to look into what are the structures I will be able to get from these transformation. Okay. So these structures we are going to call as canonical forms. Canonical forms. Okay. Canonical form means that there is a standard structure. There is a standard structure, or it is a standard form, which you can use to represent mathematical objects. The mathematical objects may be a function or a matrix or anything. So if I can write this some mathematical objects like functions or matrix in some standard form, then I call that form as a canonical form or a standard form. That's it. This form is not very new to you. You are already familiar with such canonical forms. One of such canonical form is the reduced row echelon form. So you will reduce all this, the vectors, all the columns in this manner, such that the main diagonal, the principal diagonals will be 1, and all the elements below the principal diagonal will be 0, and all the elements above the principal diagonal will be 0 or non-zero elements. Okay, so that you are already familiar with this. That is a standard form, okay, to bring down. So that you usually do by using these elementary, transformation, elementary operations on rows and columns. So similarly, in matrix theory, we have got some other canonical forms also. Okay, so these canonical forms, whatever I'm going to explain here, are only applicable for SO system, that is single input, single output system. So the first canonical form is this. So if you look at this, this is what is the principal diagonal. This is what is the principal diagonal. The elements just above the principal diagonal constitute the super diagonal. Okay. In this canonical form, all the super diagonal elements will be 1. Okay. So all other elements will be 0 except the last row. In the last row, you will have 0 or non-zero elements. Anything. Any real numbers you will have. Okay. So please notice that except the last row and the super diagonals are the elements. It's a diagonal formed by all the elements above the main diagonal. Okay. So in this canonical form, except this last row and this super diagonal, all the elements will be 0, and the super diagonal will be of all ones, and the last row can be of anything, ones or zeros or non-zero elements. Okay. And if you look at this B matrix, it is going to be 0, 0, 0, and only at the end you will have a 1. Okay. And if you look at the C matrix, it can have any element. Okay. So please notice that since I have taken an SASO system, the B is going to be a n cross 1 matrix, and C is going to be a 1 cross M matrix. Okay. Vector. So this is what is the first canonical form. This canonical form, I'm going to call it as first companion form. Usually this name is used in mathematics or in matrix theory. But in control theory, this particular form is known as controllability canonical form, and in short it is called as CCF. Why it is called controllability canonical form is, I told in the future we are going to study about the controllability and observability. This specific structure is going to help me to understand the controllability and observability of the systems. Okay, so that is why I call this as controllability canonical form. Okay, right. Then the next form is canonical form is this one. So here if you see the subdiagonal, this is what is a subdiagonal. The subdiagonal is the one below the main diagonal, just below the main diagonal, and the subdiagonal will be all of ones, and the last column will contain non-zero or 0 or 1, any elements. And all the other elements will be 0 in it. If you closely look at this, the second form is nothing but the transpose of the first form. That's it. And the B matrix, if you look at, it is going to be all some elements in B matrix. It can be anything, but the C matrix is going to be 0, 0, 0, 1. If you look at the B matrix of the first form and the C matrix of the second form are the transpose. Okay. And similarly, the C matrix of the first form and the B matrix of the second form are the transpose. So this form, we'll call it a second companion form in matrix theory, but in control theory, we are going to call this form as an observability canonical form. Again, this particular structure is going to help us to understand about the observability, and therefore we call this as observability canonical form, and in short it is called as OCF. Okay. There is another canonical form in which it will have only the diagonal elements and all the other non-diagonal elements will be 0, and the B matrix is going to be 1, 1, 1, 1, 1. Please note that for this condition to exist, all these diagonal elements should be distinct. Okay, this is the condition. In that case, this B matrix is going to be 1, 1, 1, 1, and C matrix can be anything. This matrix, it has got a very obvious name, that is diagonal canonical form, DCF in short. But in diagonal canonical form, we have got another variant. We call it as a Jordan canonical form. In that case, in this diagonal elements will not be distinct. it will be repeating. So in that case, there will be some change in the superdiagonal elements, and those structures we'll call it as Jordan canonical form. And I have not shown such structures here in the slide, but you can refer any book for that. I'll be focusing mostly on the controllability canonical form and observability canonical form, because they play a major role in understanding the controllability and observability. Okay. So in the following slides, we are going to focus on this observability canonical form and the controllability canonical form. Please notice that if I transform this x of t into x bar of t using a specific p matrix, I'm going to get this controllability canonical form or the observability canonical form. That depends on this value of p. Okay, yeah. So if I want to transform this original state space equation into a transformed state space equation with this matrices represented in canonical forms, what I need is I want to find out that specific P matrix. Okay, I want to find out the specific P matrix which will transform my original system or original model to controllable canonical form or the observability canonical form. Okay, so that's what we are going to see. So this is the original system, and we want to transform it to the system, this transformed system. Okay, such that the matrices A bar, B bar, C bar, and D bar are in CCF or controllably canonical form. First, we are going to take the CCF. So I'm not going to derive anything here. So how to get this form? Nothing done. So what we are going to do is we are going to see the procedure to transform to controllability canonical form and observability canonical form. So the first thing to do is to find out the characteristic equation. So obviously you can find out this characteristic equation by determinant of Si minus A. So you will get a characteristic equation in this form, and the last coefficient, otherwise the constant value, you have to take it as A0, and the coefficient of S term, you have to take it as A1, S square term A2, S cube term A3, and so on. Okay, S power n minus 1 term coefficient, you have to take it as A n minus 1. So the first thing is to form the characteristic equation. Then the next thing is you have to form two matrices. Okay. So how we should form these two matrices is the first matrix M and the second matrix is S. The first matrix M, this is how we are going to form. See, this matrix M will have the coefficients of the characteristic equation in this arrangement. So you have to start the first row from A1. A0 will not appear in this matrix. It starts only from A1. That means the coefficient of the S term. Then coefficient of the S square term A2 goes up to this n minus 1th term. Then last you have to end with 1. Okay. Then the second row is a repetition of this first row, but A1 is left out, starts from A2. The third row will be the same as the second row by leaving out A2, and it will be starting from A3. So you have to go so on like this, and up to this A n minus 1 you will come, and the last coefficient is 1. Of course, the S power n will have a coefficient of 1. So if you find this characteristic equation using this method, anyhow the coefficient of S power 1 will always be 1, and that is why it is 1. Okay, so why 1 here. So this is how we have to form the matrix M. Then you have to form another matrix S. So the S matrix have to be formed from the B matrix and A matrix in the original state space equation. Okay, B, you have to, B is going to be a column vector. So you'll put a column here, column vector here, and then you'll multiply that column vector by a matrix A. Again, you'll get another column vector here, and you have to keep on doing like this. And the number of columns what you will be getting is will be equal to the order of the characteristic equation or order of the system. For example, if it is a third order system, the size of this S matrix is going to be 3 cross 3. That means you will have 3 columns and every column will have 3 rows. Okay, so that is 3 cross 3. Anyhow, we will illustrate this with an example. So once you find this matrices M and S, then the transformation matrix is given by P. P is equal to SM, the product of the matrices S and M. That's it. So if you do that, immediately you will find the transformation as A bar is equal to P inverse AP. So you will see that this multiplication, P inverse, P is this SM, and AP now will result in this form. Okay. Similarly, B bar, C bar, and D bar also you can find in this way. Let us illustrate with an example. So let us say the matrices are A is equal to 1, 2, 1, 0, 1, 3, 1, 1, 1, and the B is a column vector 3 cross 1, 1, 0, 1. Okay, so obviously this is a third order system with 3 state variables. Okay, the first thing is we need to convert. So the point is we need to convert this model to the CCF. The matrices have to be transformed to controllability canonical form, and first step is to find out the characteristic equation. The characteristic equation you will find by Si minus A. Okay, so how do you find? Si is nothing but S 0 0 0 0. Okay, minus the matrix A. Matrix A is 1 2 1 and 0 1 3 1 1 1. Okay, the determinant of this. So this determinant is going to be, so you will get S minus 1, 0 minus 2 is minus 2, 0 minus 1 is minus 1. Okay, and similarly it is going to be 0, S minus 1, 0 minus 3 is minus 3. So this is going to be minus 1, and minus 1. Sorry, this is the last one is S minus 1. Now you have to take the determinant of this, and if you find out this determinant of this, you will get this characteristic polynomial, and you can equate it to 0. That is what is the characteristic equation. So as I told, the next thing is you have to identify the coefficients of this characteristic equation. That is constant term, you have to take it as A0, that is minus 3. Yes, the coefficient of S is A1, that is minus 1. The coefficient of S square is A2, that is minus 3. Once you get that, you have to form the matrix A and matrix S. Okay, so the matrix A and S are formulated like this because you have to start from A1. The first row has to start from A1, A2, and A3 is going to be 1. Okay, so because we have got coefficients only up to A2, and the last coefficient is S cube coefficient, it is 1, so you just end with 1. Then the second row starts from A2 and again A2 1, and the last row is 1. So in each row you have to eliminate the first term. Okay, when you go for the next row. So likewise it is easy to form this matrix M. Now you have to form this matrix X. Okay, so let us see how this matrix S can be formed. S is B, the first element is B, then the second element is AB, then the third element is A square B. Okay, so since this is a third order system, n is equal to 3, you have to stop at 2, that is n minus 1. You need not go for A cube B, that is not necessary. Okay, so you can stop at A square B. So if n is equal to 4, you have to go for another column, that is A cube B. So you have to stop at n minus 1. So what is B matrix? B matrix is a column vector 1 0 1. You have to write B in this B. Now you have to multiply this matrix A and B. That is A is AB is equal to 1 2 1 0 1 3 1 1 1, and you have to multiply with this B matrix, that is 1 0 1. If you multiply, this is a 3 cross 3 matrix and this is a 3 cross 1 matrix vector, and you will get a 3 cross 1 vector. A vector you will get if you multiply these two. That vector has to be written here. So if you multiply that, you can find that you will get 2 3 2. And similarly, A square B is what? You have to put one more A here. 1 2 1 0 1 3 1 1 1. Now to multiply these two matrices first, then that product matrix has to be multiplied with this vector. Again you will get a 3 cross 1 3 cross 1 vector. That 3 cross 1 vector you have to write it here, so you'll be able to see that you'll get 10 9 and 7. This is what is the S matrix. So having obtained this M matrix and S matrix, so you can find out the P matrix. P is equal to SM. So just multiply the matrices S and M, you get the transformation matrix. So the transformation matrix, the product of SM is equal to 3 minus 1 1 0 3 0 0 minus 1 1. Okay. So now you have to find out A bar is equal to P inverse AP. So P is already found, A is given, P is already found. You can find out the inverse of P. Okay, A is already given. So now you can find out A bar. If you do those multiplication, you will get this. Okay, so you will be able to see that the super diagonals are 1, the last row is having some elements, and obviously this is in CCF. And B bar, you will be able to see that P inverse B, that is equal to 0 0 1. Okay, so this is how we transform a given state space model into a controllability canonical form. Okay, now let us see how to transform to observability canonical form. Yeah, so here the objective is to transform the given state space model to a transformed model where A, B, C, or A bar, B bar, C bar, and D bar should be in observability canonical form, and the procedure is same, almost very similar to the first one. The characteristic equation has to be found, the coefficients have to be identified, you have to form two matrices. Here you have to form M matrix and another matrix C matrix. Okay, you'll be using the output matrix instead of output matrix C instead of the input matrix B. Okay, right. So it is going to be a column matrix. There it was a row matrix, or A square B. Now here it is CA square, and it goes up to CA power n minus 1. Okay, so you have to form these matrices, then form the transformation matrix Q. The transformation matrix is given by Q is equal to MV inverse, and once, see, the Q is nothing but the same transformation. It is a very similar to the transformation matrix we used previously as P. Just to distinguish, I have used this term Q. Okay, the transformation for P and the transformation for controllability is canonical form, I take it as P, and the observability canonical form, I take it as Q. Okay, so that's it. That P is called Q here. That's it. Okay, so Q, how we find is using this matrix M and V, that is inverse of MV. Once you find that, same thing, A bar is equal to P inverse AP. Here I have written as a Q inverse AQ, and similarly B bar is equal to Q inverse B. C bar is equal to CQ, and D bar is same as this D. Okay. Now let us take an example. Very similar case. So the A, B, C, D matrices are given. So the first thing is to find out the characteristic equation as we did. It is, since it is the same A matrix, we got the same characteristic equation. So identify the coefficients of the equation, that is A0 is equal to -3, A1 is equal to -1, and A1, A2 is equal to -3. Now form this matrix. Okay, form this matrix M as explained earlier, and let me explain how to get this matrix V. So V C A square, and since it is a 3 cross 3 matrix, this A power has to go up to n minus 1. So since n is 3, it will go up to n minus 1, that is 2. So CA cube is not necessary. This is what is the V matrix. So what is C here? It is given as 1, 1, 0. What is CA? CA is nothing but 1, 1, 0 multiplied by this matrix A. A matrix is 1, 2, 1, 0, 1, 3 and 1, 1, 1. Okay, so if you multiply this, this is going to be 1 cross 3 and this is 3 cross 1. So this, 3 cross 3, the resultant is going to be 1 cross 3 and it is going to be a row vector having 3 columns. So this answer will be 1, 3, 4. Similarly, you have to find out CA square. CA square is, you put this A matrix again here, multiply this 3 matrices multiplication, you will get another row vector as 5, 6, 10. Okay, so this is how you have to form this V matrix. So once M matrix and V matrix is formed, it is finding out the transformation matrix Q, that is MV inverse. Okay, if you do this matrix multiplication and followed by that inversion, you will get this matrix Q. Once you get this matrix Q, now it is all about the transformation. A inverse A bar is equal to Q inverse AQ, and B bar is equal to Q inverse B, and so on. Okay, so similarly you can get everything. So ultimately in this lecture, what we have seen is, if a state space model is given in x dot is equal to ax plus bu and y is equal to cx plus du, it can be transformed to some other model, and which is transformed by x of t is equal to p x bar of t. Okay, the only condition here is P is an invertible n cross n matrix. So when I do this transformation, the matrices also change. The A bar, B bar, C bar and D bar, I get new matrices as shown here. So what I find from this is, what I understood is, this transformation is not going to affect the characteristic equation, or it is not going to affect the eigenvalues or eigenvectors, and the transfer function also is not changed, and the input type behavior also is not changed by this transformation. So therefore we called this transformation as a similarity transformation. Okay, now, so since I can have so many P matrices, I can form so many P matrices. Okay, so I can represent the same system in different state space models. Okay, we ourselves understood the same state space model can be represented in CCF or OCF or DCF or JCF or any other canonical forms. Apart from this canonical forms, I can pick up any matrix for P and I can get the transformed matrix. Therefore, so the conclusion is the state space model of a system is not unique. But the point is, even if it is not unique, all the models will have the same characteristic equation, eigenvalues, transfer function, or the input-output behavior. Okay, so that's a wonderful thing about the state space model. And we understood that some transformations can result in some fixed structure, or which we can call it as canonical forms. The canonical forms are controllability canonical form, observability canonical form, diagonal canonical form, and Jordan canonical form. So out of this, we focused on controllability canonical form and observability canonical form, and we took two examples to understand how this given state space model can be transformed to controllability canonical form and observability canonical form. Okay, so here we end this lecture, and in this next lecture what we will see is how the similarity transformation can be used to get the state space model from the transfer function models. That is our real objective, that is getting the state space model from the transfer function model. So we will be able to see how this transformation could be done in the next lecture.